A brightly colored balloon drifting toward the ceiling at a children's birthday party is an object that personifies the concept of ephemeral joy. It is a lightweight, translucent sphere of latex, tugging gently at its string, seemingly possessed by a quiet, upward ambition. To a casual observer, this is merely a festive toy, a cheap container for a gas that makes voices sound like cartoon characters and lifts thin membranes of rubber into the air. However, the substance contained within that balloon is a fundamental paradox of physics, a cosmic fugitive that is currently engaged in its final escape from the planet. This substance is helium, the second most abundant element in the observable universe, yet one of the rarest and most precariously held resources on Earth. Within the thin, pressurized confines of a party balloon resides an element that is chemically antisocial, physically restless, and gravitationally unbound. The very lightness that makes it a symbol of celebration is the exact property that ensures its eventual disappearance into the infinite void of interstellar space. This exploration into the hidden mechanics of our disappearing atmosphere is supported by a community of observers who value deep scientific inquiry. Subscribing to the channel and contributing a perspective in the comments helps maintain the rigorous depth of these investigations into the materials that define our technological era. The physical behavior of helium, He, is dictated by its position as the first and most stable member of the noble gases. In the language of atomic engineering, helium is the ultimate hermit. Its nucleus consists of 2 protons and 2 neutrons, surrounded by a perfectly closed shell of 2 electrons. This configuration represents a state of total electronic satisfaction. Unlike the carbon, C, in our tissues, or the oxygen, O, in our lungs, which are constantly seeking to bond, share, or steal electrons from their neighbors to achieve stability, the helium atom is a self-contained fortress. It possesses the highest ionization energy of any element, meaning it requires a catastrophic amount of force to strip an electron away from it. This chemical indifference means that helium does not form molecules, it does not burn, it does not corrode, and it does not participate in the biological cycles of life. It exists in our world as a collection of solitary, independent atoms, drifting through the atmosphere like microscopic billiard balls that refuse to stick to anything they strike. This unsociable nature is precisely what makes the containment of helium a logistical nightmare. Because helium atoms do not bond with one another or with the materials they touch, they remain incredibly small and highly mobile. To understand the struggle of keeping helium inside a rubber balloon, one must look at the microscopic texture of the balloon's wall. To a human hand, the surface of a latex balloon feels like a solid, continuous sheet of elastic material. However, at the molecular level, latex is a tangled forest of long polymer chains, similar to a pile of loosely woven fishing nets. For large molecules like nitrogen, N2, or oxygen, O2, which make up the bulk of the air we breathe, these nets are dense enough to act as a solid barrier. But a helium atom is so tiny and moves with such high kinetic energy that it can navigate the gaps between these polymer chains with ease. This process, known as diffusion, is the reason a helium balloon inevitably loses its buoyancy after a day or 2. The atoms are not escaping through a hole in the knot. They are literally migrating through the solid walls of the rubber, slipping out into the room like ghosts passing through a screen door. This behavior is not limited to latex. Even in industrial settings, helium can diffuse through certain types of glass and even thin layers of solid steel under high pressure. It is a material that resists the very concept of boundaries, a prankster element that is constantly seeking the path of least resistance to escape any vessel designed to hold it. The most common interaction people have with this gas, the alteration of the human voice, is a masterclass in the physics of sound and medium density. It is a frequent misconception that helium changes the pitch of the voice by causing the vocal cords to vibrate faster. In reality, the mechanical frequency of the vocal cords remains almost entirely unchanged. The transformation occurs because sound travels at different speeds depending on the density of the medium it moves through. In standard air, which is relatively heavy and dense, sound moves at approximately 1,125 feet per second. Helium, being roughly 7 times less dense than air, allows sound waves to travel at a staggering 3,198 feet per second. When a person inhales helium and speaks, the vocal tract, the throat, mouth, and nasal cavities, acts as a resonant chamber. Sound waves bounce back and forth within this chamber before exiting. Because the speed of sound is so much higher in a helium environment, these waves complete their cycles much faster. This can be compared to a sports car driving on a flat, dry salt plain versus a muddy mountain road. In the less resistant environment, the speed increases dramatically. This increase in speed shifts the resonant frequencies of the voice upward, amplifying the higher-pitched overtones while dampening the lower ones. The result is the characteristic Mickey Mouse voice, a phenomenon that is technically an acoustic shift in timbre rather than a change in fundamental pitch. It is a harmless amusement that masks a deeper physical truth. The gas is so light that it changes the very way energy moves through space. However, the lightness of helium leads to a much more significant and permanent consequence: its inability to be held by the Earth's gravity. For almost every other substance on the planet, the Earth's gravitational pull acts as a permanent leash. Even lightweight gases like methane, CH4, or water vapor, H2O, are heavy enough that the Earth's gravity keeps them tethered within the atmosphere, where they can eventually be recycled back into the crust or the oceans. Helium is the great exception. It is so light that it is subject to a process known as atmospheric escape. To understand this, one must consider the kinetic theory of gases. Every atom in the atmosphere is in constant chaotic motion, and its speed is determined by its temperature and its mass. While the average speed of a helium atom at 60 degrees Fahrenheit is quite high, it is still below the Earth's escape velocity of 7 miles per second. However, the speeds of atoms follow a statistical distribution, much like a lottery. At any given moment, a small fraction of helium atoms in the upper atmosphere, the exosphere, are moving fast enough to break the gravitational leash. Furthermore, solar radiation and the solar wind provide additional energy to these high-altitude atoms, kicking them like a foot striking a ball. Once a helium atom reaches escape velocity and heads away from the planet, it is gone forever. Earth has no mechanism to reclaim helium from space. There is no helium rain, and there are no helium-absorbing plants. Every balloon that is popped, every industrial valve that is vented, and every laboratory experiment that releases this gas contributes to a total and irreversible loss of the element from our planetary inventory. This makes helium a non-renewable resource of the most extreme kind. While we can grow more trees, desalinate more water, and even recycle carbon from the atmosphere, we cannot manufacture more helium once it has left the gravitational well of the Earth. It is a finite leak in our world, a steady trickle of matter into the abyss. The irony of our treatment of helium is profound. We use it for the most trivial of purposes, festive decorations and party pranks, while it is simultaneously the most critical and irreplaceable component of our most advanced technologies. This joke gas is the only substance that allows for the operation of the massive superconducting magnets in MRI scanners, the cooling of nuclear reactors, and the pressurization of the rockets that carry humanity into orbit. We are currently consuming a multi-billion-year-old subterranean hoard of this cosmic fugitive to inflate rubber spheres that will be discarded within 48 hours. When a balloon finally shrivels and falls to the floor, it is because the fugitive has successfully tunneled through the latex and begun its long, vertical journey. It drifts upward, past the clouds,
past the cruising altitude of jetliners, and into the thin, cold reaches of the exosphere. There, it will wait for the final energetic kick from a solar photon to launch it into the interstellar medium. The helium atom, which was once trapped for eons in the dark silence of a subterranean rock formation, is finally returning to the cosmic void from which it originated. It is the only part of our daily life that is guaranteed to leave the Earth behind, a tiny, silent traveler that will still be drifting through the darkness of space long after the planet that once held it has been consumed by the sun.
The lightness of helium is not a gift of gravity, but a ticket out of it, a permanent exit from the cycle of earthly matter, transforming a child's plaything into a vessel for a one-way trip into the eternal night. The existence of helium on Earth represents a profound geological irony, as the second most abundant element in the observable universe is simultaneously one of the rarest substances found within the planet's crust. In the grand inventory of the cosmos, helium constitutes approximately 24% of all elemental mass, a primordial leftover from the first 3 minutes of time itself. However, during the chaotic assembly of the solar system, Earth was unable to retain the vast majority of its initial helium supply. Because the element is a light, non-reactive gas that does not bond with other atoms to form heavy minerals or liquids, it remained in a gaseous state as the planet coalesced. The Earth's gravitational field, while sufficient to hold on to heavier molecules like nitrogen, N2, or oxygen, O2, proved to be a, quote, 11 for helium. The solar wind, a relentless stream of charged particles from the sun, effectively swept the early atmosphere clean of its primordial helium, leaving the infant planet as a helium desert. Consequently, almost every atom of helium that humanity extracts today was not present at the Earth's birth, but is instead a product of an incredibly slow, radioactive, quote, 12, occurring miles beneath the surface. The terrestrial origin of helium is rooted in the terminal decay of heavy, unstable elements trapped within the Earth's deep interior since its formation 4.5 billion years ago. Specifically, the helium found in gas deposits is the direct byproduct of the radioactive decay of uranium-238 and thorium-232. To understand this process at the engineering level, one must examine the mechanism of alpha decay. When the nucleus of a massive atom like uranium-238, which contains 92 protons, becomes unstable, it seeks a more balanced state by shedding a specific packet of matter known as an alpha particle. This alpha particle consists of exactly 2 protons and 2 neutrons. In the language of nuclear physics, an alpha particle is nothing more than the naked nucleus of a helium atom. This process occurs with a staggering degree of geological patience. The half-life of uranium-238 is approximately 4.5 billion years, meaning it takes the age of the Earth for half of a given sample to undergo this transformation. As these alpha particles are ejected from the decaying uranium deep within the granitic, quote, 13 of the crust, they are initially moving at high speeds, roughly 5% of the speed of light. However, they are immediately slowed by collisions with the surrounding rock lattice. As they slow down, these positively charged particles attract and capture stray electrons from the environment, effectively themselves to become stable, neutral helium atoms. This is a form of subatomic __quote _15 where the radioactive death of a heavy metal results in the birth of a light gas. This process can be compared to a slow, microscopic leak in an underground pipe that has been dripping for billions of years. Each __quote _16 is a single atom of helium, contributing to a subterranean accumulation that has no equivalent in the upper atmosphere. The accumulation of this gas requires a specific set of geological circumstances, as helium
is a __17__ element. Because it is so light and chemically inert, it does not dissolve in water or bond with minerals. Instead, it begins a relentless upward journey through the microscopic pores and fractures of the Earth's crust. It acts like a buoyant bubble in a dense fluid,
constantly seeking the path of least resistance toward the surface. In most places on Earth, this helium simply escapes into the atmosphere and is lost to space. However, in rare instances, the upward-moving helium encounters an impermeable, 18, such as a thick layer of halite, salt, or dense shale. These structures act as a molecular umbrella, trapping the helium alongside deposits of natural gas, CH4. To find helium, one must find a natural ___, 19___ that has remained sealed and undisturbed for hundreds of millions of years. The extraction of helium is therefore a parasitic endeavor, as it is almost exclusively produced as a byproduct of the natural gas industry. Helium concentrations in these underground reservoirs are typically very low, ranging from 0.1% to 7% by volume. To isolate the helium, Engineers utilize a process known as cryogenic distillation. Because helium has the lowest boiling point of any element, approximately 4.22 degrees Kelvin or negative 452 degrees Fahrenheit, it remains a gas long after the methane and nitrogen in the mixture have been liquefied by extreme cooling. This is a process of thermal ___20__, where every other substance is frozen out, leaving behind a stream of high-purity helium. If this gas is not captured during the refining of natural gas, it is simply vented into the atmosphere, where its journey to the edge of space begins immediately. The rarity of these deposits makes helium a strategic asset of extreme value. Unlike other commodities, where scarcity can be overcome by finding new synthesis methods, terrestrial helium is a fixed inventory of radioactive ___, 21___, accumulated over eons. There is no industrial process capable of manufacturing helium on a significant scale. It must be mined from the dwindling 22 provided by the planet's crust. When we utilize helium for a trivial application, we are effectively depleting a subterranean hoard that took the entire history of the planet to produce. It is a ___23_ resource. Once a gas field is emptied, that specific accumulation of helium will not be replenished for billions of years. Once helium reaches the surface and is released, it enters the Earth's atmosphere, where it is subject to the inescapable laws of kinetic energy and gravity. This is where the element's role as an ___24_ becomes a physical reality. The movement of gas molecules in the atmosphere is governed by a statistical distribution of speeds. At any given temperature, lighter atoms move significantly faster than heavier ones. At the top of the atmosphere, in the region known as the exosphere, the temperature can reach 1,800 degrees Fahrenheit due to direct solar radiation. At these temperatures, a significant portion of helium atoms gain enough kinetic energy to exceed the Earth's escape velocity of 7 miles per second. This process, known as Jean's escape, acts like a cosmic drain. The helium atoms at the fringe of our atmosphere are literally, 25 into the vacuum of space. This loss is accelerated by a secondary mechanism known as the, 26. Because helium atoms are easily ionized by the high-energy ultraviolet light from the sun, they become positively charged. These ions are then caught in the Earth's magnetic field lines, which funnel them toward the north and south poles.
There, the electrical and magnetic forces act like a giant subatomic _27_, accelerating the helium ions and flinging them out of the atmosphere along open magnetic field lines. This is a continuous, invisible geyser of matter,
a steady stream of the second element of the periodic table being ejected into the blackness of the solar system. The cosmic accident of helium on Earth is that it exists here only because of a temporary _28_ in its escape. We are living in a rare window of time where we have access to the gas that was trapped beneath the crust, but we have no way to hold on to it once it is released. We have intercepted a cosmic traveler during a brief pause in its multi-billion-year journey from the nucleus of a uranium atom to the depths of interstellar space. To look at a balloon or a cooling system is to look at a substance that is fundamentally incompatible with the planet's gravity. It is a material that is __29_, a guest from the radioactive basement of the Earth that is destined to return to the universal abundance from which it was once excluded. Each atom we use is a fragment of deep time, a piece of the _30 from a dying radioactive giant, which is now taking its final leap into the eternal void, where gravity can no longer reach it. Our high-tech civilization is built upon the back of this fugitive, utilizing its unique thermal properties while it is still within our grasp, knowing that every valve opened is a door that leads to an absolute and permanent exit. The identification of helium represents a unique inversion in the history of science, marking the first and only time an element was discovered in the depths of space before it was ever found on the surface of the Earth. This 27-year period of scientific absence began on August 18th, 1868, during a total solar eclipse that was visible across the Indian subcontinent. To understand how astronomers could find a __31__ element across 93 million miles of vacuum, one must look at the physics of light through the analogy of a universal barcode. Every element in the periodic table, when heated to a gaseous state, emits or absorbs light at very specific, unchangeable frequencies. If a beam of white light is passed through a glass prism, it spreads into a rainbow. However, if that light comes from a burning element, the rainbow is interrupted by distinct dark or bright lines. This is a spectral signature, a physical fingerprint that cannot be forged. During the eclipse, a French astronomer named Pierre Janssen and an English astronomer named Norman Lockyer independently observed a bright yellow line in the Sun's outer atmosphere, the chromosphere. Initially, the scientific community assumed this was the signature of sodium, a common metal that produces a similar yellow glow. However, upon closer inspection, the line was found at a slightly different wavelength that did not correspond to any known substance in the terrestrial inventory. Lockyer, realizing he was looking at an entirely new form of matter, concluded that this substance existed only in the high-heat, high-pressure environment of the Sun. He named the element helium, derived from Helios, the Greek god of the Sun. The choice of the suffix "ium" is a historical artifact of a significant scientific error. Because the element had only been seen in the Sun's scorching atmosphere, Lockyer believed it was a heavy metal, similar to sodium or thallium. He could not have known that he was looking at the lightest of all noble gases, a substance so far removed from the properties of a metal that it would eventually become the ultimate symbol of buoyancy and chemical detachment. The quest to find this __34__ on Earth became a prolonged archaeological search through the minerals of the crust. For nearly 3 decades, helium remained a theoretical entity, a substance that belonged to the stars but was seemingly absent from the planet below. The breakthrough occurred in 1895, when the Scottish chemist William Ramsay was investigating a sample of cleveite, a radioactive uranium ore. Ramsay was attempting to extract argon, but after treating the mineral with acids, he isolated a gas that produced the exact same yellow __quote_35_ that Janssen and Lockyer had seen in the Sun 27 years earlier. This was the moment the cosmic fugitive was finally apprehended on Earth. The realization that helium was a byproduct of the radioactive decay of uranium, the __quote_36_ mentioned previously, provided the first physical link between the deep history of the Earth and the chemical composition of the stars. The transition of helium from a laboratory rarity to an industrial commodity of strategic importance was triggered by a comical failure in the American Midwest. In 1903, in the small town of Dexter, Kansas, a drilling rig struck a massive geyser of natural gas. The local population, anticipating a windfall of wealth and a source of fuel for lighting and heating, organized a celebratory event to __quote_37__. In front of a large crowd, a burning hay bale was thrust into the roaring stream of gas. To the shock and embarrassment of the townspeople, the gas did not ignite. Instead, it immediately extinguished the flames. The well was producing, quote, 38, quote, that would not burn. A subsequent chemical analysis by the University of Kansas revealed that the gas contained nearly 2% helium. This discovery proved that the Earth's crust held massive, concentrated reservoirs of the element, trapped for eons beneath impermeable layers of rock. By the early 20th century, the, quote, 39 of helium moved from the oil fields to the halls of global power as the era of the airship began. Before the development of reliable airplanes, massive dirigibles, zeppelins, was seen as the future of long-distance transport and aerial warfare. These vessels relied on the principle of buoyancy, utilizing a gas that was lighter than the surrounding air to generate lift. For most nations, the only available lifting gas was hydrogen, H2. Hydrogen is the lightest element in the universe and provides excellent lift, but it possesses a fatal chemical flaw. It is highly flammable. Because a hydrogen atom has a single __quote_40_ electron, it is constantly seeking a partner. When exposed to a spark in the presence of oxygen, hydrogen reacts with explosive violence to form H2O. Helium, because of its __quote_41_ of 2 electrons, is the only non-flammable alternative. It provides roughly 92% of the lifting power of hydrogen, but is chemically incapable of burning. During World War I, the United States realized that its natural gas fields in Texas and Kansas represented a global monopoly on this __quote_42__. Recognizing its immense military potential for observation balloons and naval blimps, the US government enacted the Helium Act of 1925, which effectively nationalized the production of the gas and banned its export to foreign powers. This was the first time an element was treated as a, quote, 43, a chemical asset that was protected with the same level of security as gold reserves or naval blueprints. This American monopoly became the central factor in the most famous disaster in aviation history, the Hindenburg tragedy of 1937. The German Zeppelin company had originally designed the LZ-129 Hindenburg to be filled with helium, as they were acutely aware of the dangers of hydrogen. However, because of the US embargo and the rising tensions between the Roosevelt administration and the Nazi regime, the American government refused to sell the gas to Germany. The Germans were forced to retrofit the Hindenburg to use hydrogen. When the airship attempted to land in Lakehurst, New Jersey, a combination of static electricity and a leaking gas cell triggered the catastrophic fire that destroyed the vessel in 34 seconds. If the United States had not treated helium as a geopolitical weapon, the Hindenburg would likely have survived the spark, and the history of lighter-than-air travel might have followed a completely different trajectory. As the 20th century progressed into the Cold War and the space race, helium's role shifted from a lifting gas to an essential engineering tool for high-pressure systems. The development of liquid-fueled rockets, such as the Saturn V and eventually the Falcon 9, required a substance that could maintain pressure in fuel tanks as the propellant was consumed. To explain this on the fingers, a rocket tank is like a plastic bottle of water. As you squeeze the water out, the bottle wants to collapse. To prevent this, one must fill the empty space with a gas that will not react with the fuel and will not turn into a liquid, even at the extreme cold of liquid oxygen. Helium is the only element that fits this description. It acts as a, quote, 44, providing the structural pressure necessary to keep the rocket from buckling under the immense forces of launch. This period also saw the creation of the Federal Helium Reserve in Amarillo, Texas, a massive underground storage facility built into a natural salt dome. For decades, the United States pumped millions of cubic feet of helium into this quote, 45 treating it as a critical reserve for future wars and technological breakthroughs. At its peak, the Amarillo facility held nearly 40% of the world's entire supply. However, the end of the Cold War and the shift toward a market-driven economy led to the 1996 Helium Privatization Act, which mandated the sell-off of this reserve. This decision triggered a global market volatility that continues to this day. Because helium is a byproduct of natural gas, its price is not determined by how much we need it for MRI scanners or space travel, but by how much natural gas we are burning for heat and electricity. The historical drama of helium is a story of a substance that human beings discovered in the sun, feared as a weapon, and eventually used as a frivolous decoration. We moved from the quote, 46 in the solar atmosphere to the tragic flames of the Hindenburg, and finally to the commodification of a finite cosmic resource. Every atom of helium we possess was born from the radioactive quote, 47 of the Earth's deep crust over billions of years. Yet, we spent the 20th century treating it as a political pawn. Today, as the Federal Helium Reserve nears total depletion, and the quote, 48 are emptied, we are facing the reality that the quote, 49 is one of the most serious and limited assets in our possession. The history of helium is a testament to the fact that we often do not realize the value of a material until its quote, 50 nature takes it beyond our reach, proving that even the lightest and most quote, 51 of elements can weigh heavily on the destiny of an entire civilization. The functionality of a high-technology society is entirely dependent on the specific thermodynamic properties of helium, an element that serves as the ultimate thermal barrier between modern industry and the chaos of molecular vibration. While the public perception of helium is confined to festive decorations, its true role is found in the silent, supercooled interiors of medical facilities, semiconductor laboratories, and rocket launch pads. Helium possesses the unique distinction of having the lowest boiling point of any known substance, transitioning from a gas to a liquid at 4.22 degrees Kelvin, which is approximately -452 degrees Fahrenheit. This is a temperature only a few degrees above absolute zero, the theoretical point where all atomic motion ceases. In this extreme thermal state, helium is the only material on Earth capable of maintaining the liquid form necessary to facilitate superconductivity, acting as a cryogenic anchor for the most sensitive instruments ever constructed by human hands. The most critical application of this __quotes_52_ is observed in the operation of magnetic resonance imaging, or MRI, a cornerstone of modern diagnostic medicine. To produce the detailed images of human tissue required to detect tumors or neurological disorders, an MRI scanner utilizes a massive electromagnetic field. This field is generated by a coil of specialized wire, typically a niobium-titanium alloy, that must carry an immense electrical current. Under normal conditions, any wire possesses electrical resistance, which acts like a microscopic form of friction. As electrons move through the metal, they collide with vibrating atoms, losing energy as heat. If a standard copper wire were used for an MRI, the heat generated by the required current would be enough to melt the machine in seconds. To bypass this law of resistance, the coil must be transitioned into a state of superconductivity where electrons can flow forever without losing a single watt of energy. This state of __quote_53__ is achieved by immersing the entire magnet assembly in a giant specialized vacuum flask filled with liquid helium. The liquid helium absorbs every trace of thermal energy, slowing the atomic vibrations of the wire until the __quote_54_ disappears. This is an engineering feat of extreme isolation. The liquid helium must be kept at -452 degrees Fahrenheit, while the hospital room around it remains at a comfortable 70 degrees Fahrenheit. To achieve this, the MRI scanner is designed like a series of Russian nesting dolls with layers of vacuum, reflective shields, and liquid nitrogen surrounding the central helium reservoir. If the helium supply is compromised or boils away, an event known as a quench, the resistance in the wire returns instantly, turning the stored magnetic energy into a massive burst of heat that can vaporize the remaining liquid in a matter of seconds. Every functioning MRI scanner in the world is, in essence, a monument to the cooling power of helium, a device that allows us to see inside the human body only because we have mastered the art of holding the coldest liquid in the universe. In the realm of aerospace engineering, helium acts as the invisible mechanical __quote_55_ that allows liquid-fueled rockets to reach orbit. A vehicle like the Falcon 9 or the Space Shuttle is essentially a collection of thin-walled tanks filled with hundreds of tons of liquid oxygen and rocket fuel. As the engines consume these propellants at a rate of several tons per second, the pressure inside the tanks begins to drop. If the pressure falls too low, the tanks, which are pressurized to maintain their structural integrity, would collapse under the immense aerodynamic forces of the flight, much like an empty plastic water bottle being crushed in a hand. To prevent this, engineers must fill the empty space in the tanks with a gas that is lightweight, non-flammable, and capable of remaining a gas even when in direct contact with the __quote_56_ liquid oxygen. Helium is the only element that meets these rigorous engineering requirements. It is a __quote_57_ gas, meaning it will not react with the fuel to cause an accidental explosion. More importantly, its incredibly low boiling point ensures that it will not turn into a liquid or freeze into a solid when it is pumped into a tank of liquid oxygen at -297 degrees Fahrenheit. In this capacity, helium acts as a __quote_58_ pushing the fuel into the engines with a steady, unyielding force, while simultaneously providing the internal underscore underscore quote underscore 59 underscore underscore that keeps the rocket from buckling. When a rocket is seen venting a white cloud on the launch pad, it is often a management of these high-pressure helium systems. Without the unique refusal of helium to freeze or react, the modern era of satellite communication and space exploration would be physically impossible,
as no other gas could survive the thermal extremes of a cryogenic rocket engine. The manufacturing of the digital world is equally dependent on the inert environment that only helium can provide. In the production of semiconductors and fiber optic cables, the presence of even a single oxygen or nitrogen molecule can introduce defects that ruin the final product. During the quote 60 of a fiber optic cable, a process where a thick glass rod is melted and pulled into a strand thousands of miles long, helium is used as a high-speed cooling medium. Because helium has a very high thermal conductivity for a gas, it can strip heat away from the glass strand much faster than air, allowing the fiber to solidify into a perfectly smooth, defect-free structure. Similarly, in the quote 61 where silicon wafers are etched, helium is used to create a sterile,
non-reactive atmosphere that allows for the creation of transistors that are only a few atoms wide. The high-speed internet and the processing power of modern computers are direct byproducts of helium's ability to manage heat and chemistry at the atomic scale. The unique physical behavior of helium even extends to the boundaries of human physiology in the field of deep-sea diving. When a diver descends to depths of several hundred feet, the increased pressure causes the nitrogen in standard air to dissolve into the bloodstream and fatty tissues, leading to a dangerous state of confusion known as nitrogen narcosis. To reach the deepest shipwrecks or underwater oil rigs, divers use a specialized gas mixture called heliox, where the nitrogen is replaced by helium. Because a helium atom is significantly smaller and less quote 62 than a nitrogen molecule, it does not interact with the nervous system in the same way, allowing the diver to remain clear-headed under immense pressure. Furthermore, because helium is so light and has such low viscosity, it is easier for the diver to breathe in the high-density environment of the deep ocean. This is the only application where the quote 63 of helium is an industrial byproduct rather than a prank, as the high speed of sound in the helium-rich lungs is a constant feature of life in a deep-sea habitat. The manufacturing of high-purity metals and specialized welding also relies on the quote 64 property of helium. In tungsten inert gas, TIG welding, a stream of helium is used to surround the electric arc, creating a quote 65 of inert gas that prevents the molten metal from reacting with the oxygen in the air. This allows for the creation of the incredibly strong, clean welds found in nuclear reactors and high-performance racing cars. In this role, helium acts as a molecular quote 66 standing between the vulnerable liquid metal and the corrosive atmosphere. Despite this unparalleled utility, the quote 67 of the modern world is currently facing a supply crisis governed by the laws of geology and economics. Because helium is only captured as a byproduct of natural gas extraction, its availability is dictated by the energy market rather than the needs of hospitals or space agencies. We are currently utilizing a resource that took billions of years to accumulate in the Earth's crust to perform tasks that range from the trivial to the existential. Each time an MRI scanner is filled or a rocket is launched, we are consuming a portion of a fixed terrestrial hoard. The hidden role of helium in the 21st century is that of a quote, 68, It does not appear on the spec sheets of our smartphones or the labels of our medications. Yet it is the material that makes their production possible. It is the only substance that can navigate the extremes of the thermal world, moving with ease from the absolute cold of a superconducting magnet to the intense heat of a rocket engine. It is a gas of uncompromising physical standards, refusing to bond, refusing to freeze, and refusing to stay on the planet once its work is done. We have built our most advanced technological systems on the back of this quote 69 gas, relying on its unique atomic profile to push the limits of medicine, computing, and exploration. The quote 70 is not in the voice, but in the fact that we have built such a profound dependence on an element that is fundamentally a quote 71. A material that is literally slipping through our fingers and into the void, even as we use it to build the future. Without the constant, cooling presence of helium, the high-speed, high-definition world of the present would slowly grind to a halt, succumbing to the heat and friction that this element was born to suppress. The ultimate destiny of helium on Earth is defined by a physical reality that separates it from every other substance utilized by human civilization. It is an element without a planetary return path. While the modern economy is increasingly focused on the concept of sustainability and the circular recycling of materials, helium remains the only resource for which no quote 72 exists. Carbon moves from the atmosphere into the tissues of plants and eventually returns to the air through respiration or combustion. H2O evaporates from the oceans, forms clouds, and returns as rain in a continuous loop that has functioned for billions of years. Even the most complex metals can be recovered from the soil and repurposed. Helium, however, follows a strictly linear trajectory that begins in the dark, radioactive basement of the Earth's crust and concludes in the infinite vacuum of the interstellar medium. This one-way trip ensures that helium is the only part of our daily lives, from the gas in a child's balloon to the coolant in a hospital's MRI scanner, that is guaranteed to leave the planet behind forever. It is the ultimate cosmic fugitive, a material that humanity has intercepted for a brief historical moment before it completes its final escape from the Earth's gravitational well. The mechanism of this escape is a consequence of the element's atomic mass and the laws of thermodynamics. To explain this on the fingers, every molecule in the air is moving at a speed determined by the surrounding temperature. In a gas mixture, the energy is distributed evenly. But because a helium atom has an atomic mass of only 4 units, it must move much faster than a heavy nitrogen molecule, 28 units, or an oxygen molecule, 32 units, to maintain the same energy level. In the lower atmosphere, these fast-moving helium atoms are constantly colliding with their heavier neighbors, which keeps them quote 74 down. However, as helium drifts upward into the thinnest reaches of the atmosphere, the exosphere, the density of the air drops to nearly zero. In this region, there are no longer enough collisions to slow the helium down. If a helium atom is struck by a high-energy photon from the Sun, its speed can instantly exceed the Earth's escape velocity of 7 miles per second. Once this threshold is crossed, the atom is no longer tethered to the planet. It effectively, quote, _75 into space, a process known as Jean's escape. This atmospheric leakage represents a permanent loss of terrestrial matter. Every time a valve is vented at a rocket launch or a balloon pops at a party, the Earth becomes slightly lighter. We are currently presiding over the final depletion of a subterranean hoard that took the entire 4.5 billion year history of the planet to accumulate. This creates a fascinating and somewhat tragic archaeological perspective. When future researchers, or even a different sentient species, examine the chemical remnants of human civilization, they will find the oxidized traces of our steel, the microscopic fragments of our plastics, and the isotopic signatures of our nuclear waste. But they will find almost no trace of the billions of cubic feet of helium we consumed. The helium will have left no quote, _76 behind. It will have migrated through the atmosphere and vanished into the solar system long before the first skyscraper turned to dust. In this sense, helium is our most honest but invisible biographer, the only part of our high-tech era that is physically incapable of remaining a part of the Earth's geological record. The journey of these escaped atoms does not end at the fringe of the atmosphere. Once a helium atom enters the interstellar medium, it becomes part of the vast, dilute, quote, 77, quote, of gas and dust that fills the galaxy. Because helium is chemically inert, it will never react with other elements to form complex molecules. It will not become part of an organic life form or a distant ocean. It will simply drift as a solitary, neutral particle for millions or even billions of years. It may eventually be drawn into the gravitational pull of a new star being born in a distant nebula, where it will join the primordial helium created during the Big Bang. In that environment, the helium atom that once cooled a superconducting magnet in a 21st century hospital will be subjected to the same intense pressures and temperatures that characterize the heart of a sun. It will have returned to its original home, the high-energy laboratory of the stars, after a brief and accidental interlude as a prisoner of the Earth's crust. The quote 78 of helium's existence, the funny voice and the floating balloon, is a mask for its role as a harbinger of planetary change. The rate at which helium is escaping is a measurable metric of the Earth's relationship with the vacuum of space. While we currently have access to concentrated pockets of the gas, these are geological anomalies. Once the current reserves in Texas, Qatar, and Russia are exhausted, the only way to obtain helium will be to extract it directly from the atmosphere, where it exists in a concentration of only 5 parts per million. To explain the difficulty on the fingers, this would be like trying to find a single specific grain of red sand in a 10-ton truck of white sand. The energy required to perform this extraction would be so immense that it would exceed the utility of the gas itself. We are rapidly approaching a quote 79, where the high-technology applications that rely on this element, quantum computing, aerospace engineering, and advanced medical imaging, will become physically and economically impossible. The quote 80 will have won, having successfully evaded our ability to capture and hold it. Looking into the deep future of the solar system, the story of helium takes a final, dramatic turn. In approximately 5 billion years, our sun will exhaust its primary fuel of hydrogen and begin to fuse the helium that has accumulated in its core. This quote 81 will signify the sun's transition into a red giant. As the sun expands, it will consume the inner planets, including the Earth. At this point, the physical distinction between the terrestrial helium, forged in our radioactive rocks, and the solar helium, forged in the heart of the sun, will vanish. The Earth will be vaporized, and every atom of helium that was ever trapped beneath our soil or released into our sky will be reintegrated into the solar atmosphere. The quote 82 will be caught by a much larger and more powerful gravitational master. The atoms of helium that were used to launch the first rockets of the 20th century will be heated to millions of degrees, becoming part of the final, brilliant glow of a dying star. Even in the ultimate fate of the universe, the hypothetical quote 83 helium plays a stable and enduring role. Because it is one of the few elements that does not decay and does not react, it is a quote 84 of matter. In an incredibly distant future, long after the stars have gone dark and the black holes have evaporated, the universe will be a cold, expanding void filled with a very thin gas of stray electrons, protons, and helium nuclei. Because helium is so thermodynamically stable, it will be among the last surviving structures of the material world. It is the second element of the periodic table, and it may very well be the second to last thing to exist. The atoms of helium that we treat with such casual disregard today are among the most durable objects in the cosmos. They are indestructible, unchangeable, and completely indifferent to the passage of time or the rise and fall of civilizations. The legacy of helium is therefore a lesson in the limits of human control. We have spent a century mastering the extraction and utilization of this quote 85 gas, building a world that thinks, sees, and explores using its unique thermal properties. But we have never truly, quote, 86 it. We have only borrowed it as it moved through its multi-billion-year escape plan. Every gram of helium, currently in a cylinder or a tank, is a hostage that is constantly looking for a microscopic fracture to exploit. The quote 87 element has provided us with the tools to build a high-tech society, but it has refused to stay and see the results. It is the only material that reminds us that the Earth is not a closed system, but is a small, leaky vessel in a vast and hungry universe. When we release a helium balloon and watch it disappear into the blue sky, we are not just seeing a toy move out of sight. We are witnessing the only permanent export of our planet. That balloon represents a tiny subtraction from the Earth's total mass, a small piece of the world that is guaranteed to survive the end of the world. Through millions of years, the helium atoms of our era will continue to drift through the void, silent and non-reactive, carrying no memory of the parties they decorated or the lives they helped save. They will remain as pure and as noble as they were in the first moments of the universe, a permanent signature of the human moment that has been written into the stars. The joke gas will have the last laugh, outlasting our empires and our planet, a tiny silver-white thread of order moving forever through the eternal night of the cosmos. Our high-tech civilization is merely a brief resting stop for a material that was born in the Big Bang and is destined to witness the end of all things, proving that the lightest of all elements carries the most significant and enduring weight in the story of the universe.